computing is taking a serial program, something that you do step by step by step, 1, 2, 3, 4, 5, and understanding how many of those steps can you run at the same time. Maybe 1 has to be run first, but 2, 3, and 4 can be run at the same time. Parallel computing allows us to do that. It's like making a sandwich. First you get your slice of bread, then you butter it, and then you put jam on it, and then you put the other slice on. Well, what about if you need to make 10 sandwiches? You could do all of those at the same time if you have 10 different people doing them. This is the idea behind parallel computing, is you can quite often calculate things at the same time rather than one after the other. And it's understanding how you can do that and when you can do that. And that's a big challenge with parallel computing, is actually understanding what can be parallelized is our single biggest challenge. Parallel computing is now everywhere. Even your mobile phone has multi-cores and has the ability to do hyper-threading. But we need to take advantage of that. The majority of applications that you run are still single-threaded. And certainly for the programmer in a scientific environment, where they're programming in addition to their day job, which is being an expert in the science question that they're answering, they don't have the time to learn how to do parallel programming, which is a very complex skill in its own right. However, everybody now has access to this technology, so we need to be making use of it. There are lots of cores on your laptop that are probably sitting idle. Every university pretty much now has a small cluster, or even some of them have some of the biggest clusters in the world if they're a big university. And then you have the fastest supercomputers in the world, the top 500. And increasingly the access to these is growing. But that means that we need to make sure that the software that's being used on them is able to take advantage of this, which is often not done.